Hello, everyone. I'm Peter Kish, a PhD student at the University of Warwick, and I'll be presenting a research with my supervisor, Sayan Bhattacharya, on the deterministic rounding of dynamic fractional matchings. So let's just go through the preliminaries first. We will be talking about dynamic graph algorithms. And in this setting, we have an n-node graph, a simple graph, and edges are inserted and deleted over time. We will be maintaining some solution to a optimization problem. In this case, it's going to be matching. And our goal is to minimize the update time, which is defined as the time spent updating our solution after each update to the data structure, each deletion or insertion. In this talk, we will be talking about amortized update times, which is the average update time over a series of updates. And this is how one should imagine it. Right. In the dynamic matching problem, which we will be focusing on, we are trying to maintain a large disjoint subset of edges, which compares well to the maximum matching size, which we will call mu of g as usual. And we will say that an algorithm is an alpha approximate if it maintains a matching m, which satisfies that its size multiplied by alpha is greater than mu of g. Right. And just to give an intuition how this could be done, for every dynamic problem, there's a trivial algorithm, which is just the following. At every update to the data structure, just rerun your favorite static algorithm to update your output. And for example, in a case of a 1 plus epsilon approximate matching, this will just simply take order m over epsilon time using any standard approximate matching algorithm. Our goal is to be way faster than the obvious, right? And just to give an intuition how fast the results can be achieved, we will show how can you do something which which has update time proportional to the maximum degree instead of the number of the edges, which is sparse graph. There's a huge gap between the two, obviously, or any graph actually. So we will show how to maintain a maximal matching in order delta time, where delta is an upper bound on the maximum degree of the graph at all times. And a maximal matching, by the way, is just a matching which cannot be extended by any edge in the graph without breaking vertex disjointness. And it's for a simple fact that such matchings are too approximate. And to see how to maintain such a matching, assume we already have a maximal matching and assume we are maintaining the match status of all vertices. If an edge is inserted into the graph, we can simply just check whether it can be used to extend the maximal matching we currently have. That will take constant time. In case of deletions, we need to do a bit more work because assuming the deleted edge was part of our matching. If it wasn't, we don't have to do anything. But if it was, we have to check both of its endpoints, whether any of the edges incident on them can be used to extend our matchings. But then again, this can be done just time proportional to the number of edges incident on the endpoints of the deleted edge, so in order delta time, essentially. Therefore, we can have a very simple order delta to approximate algorithm this way. The goal in dynamic algorithms tends to be to have constant or polylog n update time algorithms, and the intuition behind this is simply that this is essentially optimal because it implies a near linear static algorithm. Any almost constant update time dynamic algorithm can be used to simulate a static algorithm through just inserting the input element by element, in this case, the graph edge by edge. And then you just get a static algorithm. So this is the best we can hope for. And obviously, the greatest thing we could hope for is to have a one approximate matching, that is an exact maximum matching. But based on accepted hardness conjectures, this cannot be done in sub-polynomial time. Therefore, the ultimate goal becomes to have a 1 plus epsilon approximate dynamic matching algorithm in order polylog n or poly 1 over epsilon. But it seems to be that we are far away from this goal. So now we're going to just take a brief look at the existing results in literature. And do know that there are so many factors to optimize in the case of the dynamic matching problem that And it's also a research problem that there's just quite a lot of results to choose from, because above the usual aspects of algorithms, running time, approximation ratio, amortized worst case, randomized deterministic, we also have 3 extra settings: incremental, decremental, and fully dynamic, where incremental stands for only edge insertions, decremental stands for only edge deletions, and fully dynamic stands for the combination of them. By the way, this particular result will hold for all 3 of these settings. And this yields, because of this, there are just a number of results out there, but the general pattern is the following. There are some interesting polytime algorithms achieving better than 2 approximation, or even exact maximum matching. And there is a rich literature on polylogarithmic algorithms. There are a lot more randomized algorithms which can actually maintain a maximal matching, which is exactly 2 approximate, but there are also amortized constant 2 plus epsilon approximate randomized algorithms with additional properties which are very useful. And there are some slower deterministic algorithms which came a bit after the discoveries of their randomized counterparts. There are also algorithms for the special cases of incremental and decremental graphs, which are essentially optimal in a sense that they are almost constant time and achieve 1 plus epsilon approximation. So those 2 settings seem to be easier. Note that there were a few things which could not be achieved deterministically before, such as essentially maintaining an arbitrary low polynomial with arbitrary low polynomial update time, maintaining a better than 2 approximate fully dynamic matching, and also deterministic algorithm for decremental matchings in bipartite graphs. And this begs the question whether randomization actually provides any power. How much power does it provide? How necessary it is? Since lower bounds based on hardness conjectures, which are used in dynamic algorithms to get hardness bands, don't really differentiate between randomized and deterministic algorithms. So this is not an obvious question. And our result essentially shows that randomization matters less than previously known. Okay, so let's just get more precise about the problem setting now. We will be talking about fractional matchings for the most part. And a fractional matching is just a linear programming relaxation of a matching, where instead of assigning values 1 or 0 to the edges, we will be assigning values between 0 and 1. But we will be expecting the same constraint that around the given vertex, edges incident on a particular vertex, will have weights adding up to 1, which is essentially equivalent to vertex disjointness in the case of integral matchings. We will refer to the size of a fractional matching as just simply the sum of the weights on their edges. And it's a folklore fact that in bipartite graph, the size of a fractional matching is the same as the size of an integral matching. And while our results in a paper will hold for general graphs, for the purposes of this presentation, we'll be talking about bipartite graphs exclusively. Do note that in general graphs, things are a bit more complicated because there's a 3/2 integrality gap, as this triangle example demonstrates, between fractional and integral matchings. Okay, so just to show why our result is actually important, or why we're focusing on it, we will explain a very popular way to design dynamic matching algorithms. They usually consist of 3 steps. And in step 1, we maintain a fractional matching instead of an integral matching on a graph. And step 2, we reduce or sparsify the edge sets of this fractional matching. And in step 3, we maintain an integral matching on this sparsified edge set. Essentially, in step 1, we solve the linear programming relaxation of the integral matching problem. And in step 2 and step 3, we ran that matching to an integral solution. Why do we focus on fractional matchings instead of integral matchings? Well, the simple answer is that it seems to be an easier problem and there are stronger results out there for it. And to see why that could be, just consider an almost k-regular graph where degrees lie between k times 1 minus epsilon and k, so it's dynamic, there's some fluctuation. And maintaining an integral matching in such a graph is by far not obvious, but Maintaining a fractional matching fully dynamically is clear. We just assign the same uniform weight to all edges, and we will get an almost optimal solution. So there are many instances where fractional matching seems to be easier, and in general, there are just stronger results out there. Step 2 is what we will be focusing in this talk, and is the sparsification of the fractional matching, where we want to reduce the edge set of the fractional matching without losing much of its size. That is essentially, we want to define a smaller edge set on which we can define a valid fractional matching, which is about the same size as the original. For this problem, there have previously only been randomized solutions, and we show deterministic execution. Just to imagine how this could be done, let's just briefly take a look at what R et al. Did. And essentially, solutions previously relied in forms of random sampling. And to imagine how could that look like, just sample each edge with probability W phi times log of n. And this way, the expected degree of each vertex will be about its weight in the fractional matching times log of n. And on such a graph where everybody's degree would be its weight in the fractional matching times log of n, we could just define a fractional matching of 1 over log n uniformly, and it would have the approximate size we're looking for. So the actual execution is more sophisticated, but you can see how randomized sampling could be used to achieve some kind of sparsification. Do note that the simple approach was not robust against adaptive deletions. That is, if the updates would have happened to delete exactly the edges we sampled, we wouldn't have had time to rebuild or reconstruct the matching quick enough. And David Weiss has shown an interesting solution to sample edge colorings instead of edges to avoid this issue. Right. And step 3 is when we solve the dynamic matching itself on the sparsifier. And it seems to be an easier problem to solve dynamic matching on the sparsifiers. And to this, the little example we had about maintaining a maximal matching on a low degree graph can give an intuition why that is. And in fact, there are very strong results on maintaining dynamic matchings on sparsifiers. The canonical results from Gupta and Peng, when they showed how to maintain a 1 plus epsilon approximate matching in about order maximum degree time. Note we will be using a different result, but more on that later for step 3. Okay. Point here is that step 1 and step 3 has very nice deterministic implementations, whereas step 2 in this 3-step process only had randomized solutions. Therefore, solving that deterministically instantly determinizes the whole process. And this is the main result of our paper, sort of formalized, somewhat formalized here, but not too formally. Obviously, details in the paper. Essentially, given a fractional matching W, undergoing edge deletions and insertions, that is a fully dynamic one, we can maintain a fractional matching on a reduced edge set, which has about the same size. The fractional matching itself, on the other hand, the edge set of the fractional matching will have very low arborosity, and I will explain why is that later. And we can do this deterministically in O tilde 1 update time. Again, tilde as previously hides log n factors and poly 1 over epsilons. And as this is a step 2 in the step 3-step process, it has instantaneous results in applications right away. 3 of them, in fact, listed here, which we have found. We're interested to see if there are any more, is that we can get 1 plus epsilon approximation for the decremental bipartite dynamic matching problem in O tilde 1 time, 2 minus delta approximation, so sub-2 approximation in arbitrary low time, fully dynamically in bipartite graphs, deterministically, of course, and 2 plus epsilon approximation, fully dynamic matching in low polylogarithmic time, in general graphs this time. And this was an improvement to log to the 4n from log to the 21n. Right. First, we will now discuss a static algorithm for deterministically random fractional matching. First of all, let's just note that it is enough to focus on uniform matchings if we allow some log factors. And this is because we can round fractional matchings to the closest 1 over 1 plus epsilon to the I value for some small constant epsilon. And this way, each edge will lose at most some epsilon fraction of its weight. On the other hand, we will be able to sort the edges into some log n over epsilon different weight categories. And this allows us to consider uniform fractional matchings. This is a standard method in this field, and we will be focusing on uniform fractional matchings from this point onwards. To be very specific about the problem in the uniform setting, we have a fractional matching mapping the edge set to some lambda, which is a constant, and our goal is to find a fractional matching on a subset of E, which is mapping edges to 0, 1. Their sizes are about the same. On every vertex, the new matching takes at most the weight of the previous matching, and the edge set is small. Imagine it as having small maximum degree. And the intuition is the following. If we were to have some linear time process, which manages to halve the degree of every edge, that is just to select a subset of edges which has approximately half the degree on every vertex, then we could simply just take that half and multiply each edge weight by 2, and we would essentially achieve what the problem wants. We would have reduced the edge set by half and maintained weights vertex-wise. And we could just repeat this some polylog time and get our sparsifier. We will not be able to achieve exactly this, but we'll see how close we can get. To see how this could be done, just decompose the graph into arbitrary maximal walks. That is, just start from a vertex, as the image shows, and just keep on walking in both directions as long as we can. Then remove the walked edges and repeat the same process on the rest of the graph. And you can cover the whole graph this way. Once the whole graph is covered in walks, in every walk, just drop every second edge. And the intuition here is that even degree vertices will have their degrees exactly halved in this process, as every walk will enter them and leave them at every time. And odd degree vertices will be approximately halved, as there can be exactly one walk entering but not leaving them, or vice versa. Therefore, if we just do what we said, that we drop half of the edges and double the weights on the remaining edges, we have effectively sparsified the graph. And we can just repeat this a polylog number of times. Right. Each iteration can be done in linear time. This is essentially a walk. And since each iteration halves the edge that we have to walk, the running time will follow a geometrically decreasing pattern. So it will essentially be linear over all iterations. That's very nice for us. Now, the slight issue is that on odd degree vertices, the halving is not precise. And in specific on low odd degree vertices, we will generate too much slack. On the bottom left vertex in this particular image, we have multiplied the weight by 4, for example. So we need to find a way to get around this problem. How do we go about this? Well, if a vertex happen to have small degree in the sparsifier, then maybe we can just keep all edges incident on it, because it just doesn't contribute too much to the edge set. And this is exactly what we're going to do. Before every degree splitting up procedure, we will try to sort out vertices which are risky to split in, because we will receive a bad approximation. That is, we will initialize all vertices as active. And at the start of each degree splitting procedure, we will walk the graph and remove vertices which don't have enough active neighbors iteratively. Once we're done with this, we mark them as passive. We will freeze the weights of all edges incident on them. Those edges will be part of our sparsifier with the weight they currently have. And we will proceed with degree splitting on the remainder of the graph. This can be done in linear time, as this is again essentially a walk, and the endpoints of each edge will be checked exactly once one time for having the right amount of active neighbors. And we can just repeat or just commence with degree splitting on the remainder of the graph and just repeat this process again and again. And this way we have achieved actually a nice approximation in every vertex, not just large or even degree vertices. Now, there's a slight issue, on the other hand, that the sparsifier we receive this way will not have bounded maximum degree, which would have been very nice. To see why this is, just consider a case of a star. If we were to take a star, before the first iteration, every vertex would eventually be moved passive. So every edge would remain in our sparsifier, and obviously the large degree vertex would not have bounded maximum degree. On the other hand, our sparsifier will admit a low out degree orientation. And to see why this is, just any time a vertex is moved to the passive set, orient its unoriented edges towards its active neighbors. There can't be too many of these, since this is why we move the vertex to the passive set. Therefore, in this orientation, every vertex will have low out degree, which means that the sparsifier has low arboricity. And lucky for us, there is actually a result slightly stronger than Gupta and Peng's out there, which allows us to maintain a 1 plus epsilon approximate integral matching on a low arboricity sparsifier. And we just be using that black box solution instead of the popular Gupta and Peng solution. As far as we know, this is the first algorithm using this black box solution for step 3. Okay, so the interesting question now remains, how do we turn this process dynamic? And let's separate insertions and deletions because they're just a bit different. And insertions are simpler, just because this data structure is very robust against insertions. So assume that the graph has some m edges to begin with, and then the total size of the matching will be some lambda times m at this point. And assume some epsilon m insertions have happened. Well, the matching size will become 1 plus epsilon m times lambda, which means that if we didn't even touch our sparsifier, it will still be 1 plus epsilon approximate, which means that at this point we can just reconstruct our sparsifier in linear time, and throughout the whole process we will be 1 plus epsilon approximate to the proper solution, and this will result us in a amortized 1 over epsilon update, and which is completely fine for us. Now, edge deletions are a bit more subtle. Just the sparsifier is less robust against deletions than it is against insertions. And the reason why this is because in the resulting sparsifier we return at the end, some edges will be representing very high weight. And if those edges would happen to be deleted, we would be somewhat in trouble. But we can again use amortized rebuilds, just be a bit more subtle about it. There will be, as degree splitting operations proceed, there will be higher and higher layers of the data structure. And in higher layers, edges receive larger weight, and therefore the higher layers are less robust. On the other hand, the sizes of these layers are also decreasing, the number of edges in them. And these two things will balance themselves out. The robustness will be exponentially decreasing. On the edge set, also, on the other hand, the edge set will also be exponentially decreasing, which means that amortized rebuilds will have about the same time. And essentially, this is what we're going to be doing. We will be monitoring every layer's state at any point, and if any of them becomes too damaged, we wait until that point, like here, layer 2 seems to be very damaged. We just rebuild every layer from that point upwards. And due to them having smaller edge sets, this will still result in constant amortized update time per layer, and we just do this with every layer, incurring some log factors. So the moral of the story here is that we can again just use amortized rebuilds. Okay. Now let's just talk about some possible future future research directions. As mentioned, as far as we know, every dynamic matching algorithm using this kind of template is using the Gupta and Peng maximum degree based solution. It would be very interesting to see if there are other implementations using this somewhat relaxed version from Peleg and Solomon. Maybe we can get some stronger results. And also there are some log factors between the deterministic and randomized solutions for this problem, with this being the first deterministic one. And it's an interesting question to see whether they can be closed. The big interesting problem, which we're also very interested in, is to breach the 2 approximation barrier, which nobody really has seen how to do in polylogarithmic time. And this is a particularly exciting question since it seems to be achievable, as there are 1 plus epsilon approximate decremental and incremental algorithms in polylog update time, and there are even arbitrarily low polynomial sub-2 approximate algorithms out there. So it just seems like something which should be possible, and yet nobody managed to grasp it. Well, thank you for your time and the opportunity to present at this conference.